responsibility.
Hello, everybody. Hello, everybody. Welcome. Welcome to Green College, all of you here and all of you online. I'm Andrew Alexander. I'm a master's student in the math department, and I'm academic host here, so I'm sort of the guy who makes the coffee for the guy who makes the tea. But I'm happy to see everyone here, and I'm sure we're all very excited for this fourth installment of our Precarity and Uncertainty lecture series.
Is it turned on?
The mic.
Is it turned on?
It is turned on at max volume, but I will project as much as I can. Thank you. So as always, I'd like to begin this event by acknowledging that Green College rests on the traditional, ancestral, and unceded territories of the Musqueam people. We like to provide that reminder at the beginning of all of our events. And without further ado, I'm going to pass off the mic to Josip Kim and eventually to Paul Gustafson. So, thank you, everybody.
Hello, everyone. Thanks for attending. I'm Josip Kim, also known as the guy who makes the tea. So, as part of the Leading Scholars program here at Green College, I was particularly drawn towards this series of Precarity and Uncertainty because I'm personally obsessed with the topic of uncertainty. So, there are very few things in science or in life that we have absolute certainty about, whether it's the weather, earthquakes, the efficacy of a drug treatment, where to find the best coffee in Vancouver, etc. So this then begs the question of how to properly deal with uncertainty, as the presence of uncertainty does not mean all is lost. That's just a fact of life. So through experience, education, and so forth, like many others, I've come to the conclusion that the most logically consistent way to reason about uncertainty is through Bayesian inference, which, if you aren't familiar with it, just means you're in the exact right place. So lucky for us, there is no better guest to talk to us about Bayesian inference than Dr. Paul Gustafson, our guest speaker tonight. He's professor and head of the Department of Statistics here at UBC. His research interests are, of course, in Bayesian methods, but also in applications of Bayesian statistics to topics such as epidemiology and public health. He's a recipient of numerous honors and awards, including being a fellow of the American Statistical Association, as well as the 2020 Gold Medalist of the Statistical Society of Canada. He's also authored 2 popular textbooks on Bayesian methods, and on top of that, he's the founding co-director of UBC's popular Master of Data Science program. So let's give a warm welcome to our guest speaker tonight, Dr. Paul Gustafson.
Well, thank you so much for that kind introduction. Am I audible in the room, online? Excellent. Okay. Put that in my pocket. I should start with an apology. I wouldn't normally show up to an esteemed place like this and an esteemed audience in my jeans. But this morning on my way to work, I stepped in a puddle of deceptive depth. And these were the only emergency pants in my office. So I'm not sure if I was using Bayesian reasoning or not this morning, but I was certainly using faulty reasoning. Okay. Let's see, I guess, well, this has already been covered a little bit, but I'm very interested in Bayesian methods. I have been since graduate school back in the early 90s. And I tend to tie that in, as was mentioned, with applications to biostatistics, epidemiology, public health. And there are some other things I'm interested in here on the slide as well. In particular, let's see, does my cursor, so to speak, show up? Yeah. In particular, measurement error will come up in the presentation today. So, precarity and uncertainty, where to start? I thought we'd start with a word problem. So this might be something you would see on a undergraduate probability exam, perhaps. So the prevalence of something, blah-itis, in British Columbian adults is 1%, 1 out of 100. There's a blood test for this condition. It's known to be 96% sensitive and 98% specific. And if those words aren't familiar to you, sensitivity is just the probability that the test is correct when applied to someone who truly has the condition. Specificity is the chance that it's truly correct when applied to someone who doesn't have the condition. As part of routine screening, I tested positive. How likely is it that I actually have blah-itis? So That's the exam question. And you can work through it, or students can work through it. And by the way, this is, I think, really the only math on in my talk, so more or less. So you may have seen something like this, or maybe not, doesn't really matter, but the essence of what you want to do here is you want to use the idea of conditional probability. So here, in generic terms, we'll talk about the probability that A happens given that B happened. And we'd like to apply that to figure out what's the chance that I actually have the disease, my actual status is positive, given that my test was positive. So we want to do this calculation. And we start down, now again, this will mean more or less to you depending on how much probability you've studied, but we start down this path of, by definition, the conditional probability is the chance that both things happen divided by the chance that the conditioning event happens. And then we manipulate that a little bit. And the key thing is that we want to kind of flip things around, whereas we're ultimately interested in the way the world is, whether or not I have the disease, given the data, that my test was positive, but we want to flip that around and express it in terms of probabilities conditioned the other way around. For instance here, given that I have the disease, what's the chance my test is positive? Or given that I don't have the disease, what's the chance my test is positive? And so we work through this calculation, and that tells us where the 3 numbers on the previous slide get slotted in, and the 1% so-called prevalence goes in here and here and here, and the 96% sensitivity goes in here, and the 98% specificity goes in there, and out comes the answer. That based on this positive test, it's actually more likely than not that I don't have blah-itis. Okay, there's a 1/3 chance that I do, and double that, a 2/3 chance that I don't. And I think sometimes that even something like this is a bit surprising to people because, of course, this kind of on face value, this doesn't look so bad, right? It sounds like this is a pretty good blood test, right? 96, 98, those sounds like, pretty good. And yet, because in fact it's an uncommon condition in the population, I end up with just this data or this conclusion that there's a 1/3 chance that I have this thing, and a 2/3 chance that I don't. And I guess the point is, if you're kind of okay with this, then you're okay with Bayes' theorem, because this really is Bayes' theorem. We could maybe, and in a way, this is a poster child, or perhaps the poster child application that is kind of the gateway into Bayesian reasoning. We could maybe talk about it in a little bit more generic or formal terms. We might talk about there being a prior distribution. In our case, that's the 1 in 100 chance that if someone is picked randomly from the population being screened, that they have the disease, and a 99% chance they don't. We talk about a statistical model that describes the distribution of the data we're going to see, in this case the test result, given the way the world is. And that's this business of the sensitivity and the specificity. And then this calculation we did gets us the posterior distribution. Given that the test came back positive, there's a 1/3 chance that the patient or me has the disease. And so in a way, saying that this is a theorem is a little bit grandiose. All we've really done is use the laws of conditional probability. So on the one hand, it's, theorem dresses it up a little bit. On the other hand, Bayes deserves all the credit because he was the first one to figure out it makes sense to flip these things around and try and work from probabilities of data given the way the world is and manipulate to get probabilities about the way the world is given data. So the insight is in the application of the laws of probability. It wasn't an invention of the laws of probability. I would say it that way. All right. And then I guess I've got one more, slightly more formal version of this, thinking a little bit more statistically now. For those of you who have done statistical modeling in some form or other, we would tend to talk about there being some unknown parameters, and we tend to use a Greek letter for those, say theta. Or sometimes more in a decision theory context, people would talk about the unknown state of the world, which in our example was the unknown was whether or not I had the blah-itis. We tend to talk about specifying a statistical model that talks about how the data are distributed. So we're going to be observing something, some observable data D. How is that distributed, given the way the world is, given the value of theta? And in our case, that was this sensitivity and specificity. Kind of simple there because theta can only be it's a binary thing. It's either a no or a yes, uninfected or infected, if you like. And then as per the math 2 slides back, the posterior distribution is just the consequent distribution of the unknown state of the world, or the parameters, given that we observe whatever we observed for the data set. And, well, it's actually kind of hard to be super consistent about this, but statisticians will tend to write an uppercase D here if they're talking generically about the data that we might see, and then a lowercase d here to talk about, my test was positive, or, here's the data in my spreadsheet, sort of a thing. And I guess the other thing I'll say, depending again on what you've seen of this written down mathematically or not, sometimes this gets framed as in terms of so-called density functions. You can talk about the density of the unknown theta given the data d is proportional to the density, or sometimes this is referred to as the likelihood function of the data given the parameter times the prior density for the parameter. And in a way, we could stop here because there's nothing else to do. You've got this posterior, that's it. That is your summary of what you know after having collected this data. However, that would make for quite a short talk. So let's try and go on. Some people are saying, yeah, please stop now. No, okay. Let's see. So I'm going to try I'm going to try and do sort of a fair thing in the sense I'm going to try and advocate a little bit for doing statistics in this way, but I'm also going to talk about the criticisms a little bit as well. One thing I really like about the Bayesian approach is what I would call universal applicability. You can kind of apply this way of thinking to anything. So for the applications I would tend to work in, for instance, theta might just be some sort of drug efficacy. How much better is drug B than drug A? And then the data will be maybe clinical trial data that randomizes people to get drug A or drug B. And I would try and see what my posterior is on the drug efficacy, given that the trial data or the observational study data come in to be whatever they come in to be. In a pollster's world, and this is now more a sort of quite a stereotypical statistical situation. You think about, well, there's a population and a sample, right? And so in the pollster's world, theta is a proportion amongst all eligible voters. But of course, the opinion poll is only talking to a few people. And so the data are only coming from a few people. And in this day and age, actually, this is one thing that's gotten worse over time. It used to be that you could, as a pollster, sort of reasonably try and do random sampling because you could do things like random digit dialing when everyone had a landline and so on and so forth.
Eligible voters where? Are you talking Canada? Or
could be Canada. Yeah, you decide, right? This is.
You're using Mark Carter.
Well, okay, so yes, Canada. Let's go Canada. yes, yeah. And then a little bit like the infected or not infected, diseased or not diseased, in the criminal law forum, theta might just be the binary thing: is the person innocent? Is the defendant innocent, or are they guilty? And then D is all the evidence that comes up in the trial, including forensic evidence. And I raise this because it's actually super, super hard. And you may be aware that there have been now multiple iterations of very eminent statisticians, presidents of societies, and so on, and weighing in and saying, wait a minute, I'm not sure this conviction is safe. I'm not sure that this Bayesian... And often, I mean, there's often a lot of detail, but often the crux of it is that people aren't really thinking about the prior and the likelihood properly, and if that's not done carefully, there is a risk of a miscarriage of justice. And so you can read about that in multiple cases now. But that also speaks a little bit to, I'm hiding a lot of devil in the detail here, or sweeping things under the rug. Sure, if we're talking about a diagnostic test and whether or not I've got a disease, it's pretty easy to think about what the prior is and what the statistical model is. if I start modeling climate or complex systems or whatever it is, I mean, that's, totally orders of magnitude harder. And so, unfortunately, defensible specifications of prior distributions and statistical models, they don't tend to fall from the sky. And so you have to work hard at that and try and defend what you've chosen ultimately. And I'll have some more comments about that later on. Okay. I do want to talk about a class of problems that applied problems that I've been involved in, where I find a Bayesian approach to be particularly helpful, and I'll try and explain why I have found that. And that's in the area of measurement error. So it's very common in health research, particularly, all sorts of fields, but my examples tend to be from health, where you really want to see how some variable x is related to some other variables. It could be as simple as there's an x and a y, or it could be x and a zillion other variables, but you'd like to know how x relates to other things. But you don't actually get to measure x in your study. The best you can do is measure some surrogate for x. We'll call that x star. And this list is just kind of drawn from applied problems I've been involved in. And so x, a little bit like very much like my opening example, x could be infection status, but the diagnostic test may make errors. I've worked a little bit with folks who do nutritional epidemiology, and that is a complete minefield in terms of measurement error, as you might imagine, trying to actually figure out people's intake of nutrients by asking them what they ate is challenging, to say the best. And even when you get into things, the more sophisticated studies use biomarkers, even those aren't perfect, and so there's a lot of sort of back and forth there. Very common now, so much observational health research is now using electronic health records, which in some senses are great. So people, some of you may be aware of Pop Data BC and the data they provide. It's great in the sense that you can link a zillion things together. It's not so great in that those data were never designed to be used for research. And so you end up with challenging issues of measurement. So for instance, in one project a few years ago, the X was whether or not someone actually had MS, but the X star was some algorithm based on looking at a person's billing codes over time to make a guess as to whether or not the person had MS. And so that's where the surrogate arises. So things like that. And certainly this has been, from my point of view, this has been quite satisfying because I get to sit in a room with medical folks and try and tease out how do we build this bridge between all this complicated stuff that they know about and this Bayes theorem at the other end that I know about. And so we try and work and build priors and build likelihoods. And so that's been quite satisfying. But what I really want to get into is, just with kind of a toy example, is one thing I like about dealing with these kinds of problems in a Bayesian way is what I would call, that we get seamless integration of uncertainty due to multiple sources. And in particular, these problems are a little bit complicated off the bat because remember we talked about all the things we don't know are wedged into this theta here. So it's written as a single symbol, but it might actually be 10 things, right? 10 parameters, if you like. And we need some parameters to describe what we're really interested in, which is how the x relates to other variables that we're going to have data on. But we also need some elements in theta to talk about how good this surrogate is. How good is the x star as a surrogate for the x? And in a way, we've actually already seen something like that, right? If x were binary and x star were binary, then the sensitivity and specificity would be those parameters. But it can get a lot more complicated than that. But what I like is we kind of get the uncertainty managed for us in a principled way that is kind of, in a way, on autopilot, and we don't have to worry too much about how we do that. So I'm going to try and talk you through a toy demo of this. And the way I'll do that is I'll make up the world so that I know what's actually going on. That will make things very, very simple. But then we'll talk about what happens, in reality, you won't have that, but I'll come back to that. So we've got a made-up world here where there are two interventions and people are interested in how good one is relative to the other. So some intervention to try and improve something for some patients in some.
So how much overlap is there between the two groups then? I mean, of the 40 and 50, how much?
Oh, well, so I'm thinking that we'll think about it this way. I'm going to get data on some people who take intervention A. Maybe that's this half of the room. Others who get intervention B, that's this half of the room. And then I want to see about, how good are your outcomes compared to your outcomes. Does that make sense?
Okay.
Ish? Yes, okay. Well, let's go on and see how we make out. And so one thing we can say off the bat is that B is, we've made up this world, so we know B is better than A. We know it's better by 10 percentage points. And so we might say, well, the efficacy is 0.1 or 10 percentage points on the so-called risk difference scale. If you start talking to epidemiologists, you'll get in a tizzy because they'll start to talk about, well, do you want a difference between the 50 and the 40? Do you want a ratio? But let's just go with the difference and keep it really simple. And let's think about what would be the perfect data to have here. I wish I could do a randomized control trial. So I would flip a coin for everyone in the study, and depending on the coin, I send them to get intervention A or intervention B. And I want to be sure about my conclusion, so I'm going to do this for an infinite number of people. Of course, I can't really do that, but just bear with me. And for everyone in the study, I measure whether the intervention worked, and we'll call that W. We'll call that W is a binary variable, 1 if it worked, if the intervention worked, 0 if it didn't work. And the perfect study would give you the perfect answer. You would know exactly how good the drug is in people who, or the intervention is. You'd know exactly how well A works in the population. You'd know exactly how well B works. And so your posterior distribution is kind of trivial here. It's 10% plus or minus 0%, right? You know the answer. Too easy. But just kind of a starting point. The next best study is you don't have infinite time and resources. So your clinical trial, your randomized controlled trial, only has 1,000 patients in it. And roughly 500 of those will be sent off to get intervention A, the other 500 to get intervention B. And you can do your Bayes' theorem thing here, and you get this blue curve. So this is your posterior density, if you like, or distribution over the efficacy of intervention B compared to intervention A. And for reference, you'll notice this dotted red line is at the truth. So this is the right answer. And you see that your posterior it's not centered at the right answer, but it's not far off. But of course, it's got some width, right? Because you've got uncertainty. You only had 1,000 patients in your study, and as a result, you've got this uncertainty about exactly what the efficacy is. On the other hand, I guess on the good news side, I've also put in the prior that I've chosen to use here in green. And this is just to give you the visual impression that, yes, it's worthwhile collecting data on 1,000 patients here because your posterior in blue is much more concentrated than your prior in green. So you've learned something. Seem okay? All right. And I probably made a pedagogical error here. I probably should have actually shown you, I simulated this data in my computer. I probably should have actually shown you the data, right? There's some number out of 500 in the A group for whom it worked, and some number out of 500 in the B group.
But some would be helped by either or both, and some would be helped by none of them.
Yes, and now you're jumping way ahead of me, beyond what we're going to talk about today. But that's a very astute observation. So if you look into the so-called causal inference literature, this is exactly what they talk about. That in fact, we are all walking around. This is a good side note. The causal inference framework, some of you may have encountered, is such that we're all walking around with two outcome variables. The one that manifests if we get intervention A, and the one that manifests if we get intervention B. And absolutely, for some people, those two things are the same, and they're both one. So people improve no matter what. For others, they don't improve no matter what. But then there's this middle for whom they improve on one and not on the other, and that kind of all is hidden away behind here. And that's for the next lecture. Put it that way. Okay, but now we're going to degrade things a little bit more. So this is now our next best study. So I've still got these 1,000 people, but I don't get to, this is now where the measurement error comes in. I only get to observe a surrogate, W star, for whether or not the intervention worked. I don't get to observe the W, which is truly whether or not it worked. And now we get into this sensitivity and specificity game again, although I'm going to make it kind of simple. I'm going to take it as known that the sensitivity of this surrogate is perfect. It's the specificity that is worrisome. And if you want a little sort of narrative around that, consider that W might be something like worked means that you achieved a fitness goal. And so W equals 1 is that you achieved your goal, or the goal, and W equals 0 is not. And human nature being what it is, if you ask people to self-report on this, particularly in front of an interviewer, there's not much, for social desirability reasons, I don't think anyone who's truly a 1 is going to say they're a 0, but you can easily imagine that someone who's a 0 is going to say they're a 1. And so that would be a way in which this kind of thing could arise. You would not worry about the sensitivity. You can think that's perfect, but the specificity is the worry. And so in my computer, I simulated a new version of the data where it's not the W, it's the W star. It's the same 1,000 people, but there's this corruption with the measurement error. And I'm going to do my analysis. Now I'm going to presume that I have something in my favor here still. I'm going to presume that I do know this. I do know this specificity. It happens to be 87%. When I simulated the data in my computer, I put in 87 as the specificity. And I'm going to take that as a known thing I can use in my analysis. And when I do that, I get my posterior in blue here. And compared to the grayed out thing is the one from the previous slide. Okay. And so we see a widening of the uncertainty, as we might expect, right? This blue curve is, well, it's not quite as peaked, and therefore it's a little bit wider than the gray one. And that's because we've lost information by having the surrogate, the W star, instead of the W. Does that make some sense? However, this may still be too optimistic in the sense that I'm not sure anyone's going to point down from the sky and say, yes, the specificity is 87. So the next best study just uses the information that the specificity is somewhere between 70% and 90%, which is a reasonable forecast, right? Truly it's 87, but that's maybe all you know in the real world. And so you can kind of see where this is going. You kind of back off, and now you're really using a prior distribution for this specificity that lives between 0.7 and 0.9, and you see a further widening of your posterior distribution, right? The blue thing now is wider, lower and wider than its two predecessors. And so this kind of increased uncertainty as you make the problem more realistic. Now, the reality check, of course, is that this is not what you see in an applied problem, right? You don't get to see that red thing, which tells you what the right answer is. You don't get to see any of those gray things that are the studies that you wished you could have done. You are just stuck with that one blue thing. So that's, in sort of my world, that's sort of the only version of the study that can be actually operationalized, made to happen. But kind of along the lines of showing you how this gets wider and wider, you have some confidence that you captured all the uncertainty that you should when you portray this result. So all you can show is the green, the prior, and the blue, the posterior, but you have some faith that that blue thing is picking up all the uncertainty that's really at play. It's picking up the fact that you only had 1,000 people in your study, not an infinite number. It's picking up the fact that you only saw this surrogate W star, not the W. And additionally, it's picking up the fact that you don't actually know the specificity of that W star exactly. You only know it to plus or minus 10 percentage points. And so this is what you end up with in the real world. Does that make some sense? All right. And then just to finish that up a little bit, you might just think that, Bayesians just stare at curves all day. That's not completely true. To try and match up with, sort of more traditional statistics, we will try and quantify things a bit more. Typical thing would be you would take this posterior and you'd report some measure of its center, say its mean or its mode or its median, as the point estimate, your best guess at the parameter. And then you might use the width of this in some sense to report an interval estimate, some version of a confidence interval, except we call it a credible interval. And so you'd see things like this. We take the point estimate to be the mean of the posterior distribution. We use percentiles of the posterior distribution as a 95% credible interval, which kind of is analogous to a 95% confidence interval, but you fail stat 200 if you can't distinguish between one and the other. And in this case, you can kind of see that just based on those curves I showed you, you see that when we go from next best to next best to next best, the interval estimate gets wider just because those curves were getting wider. So this might be the sort of thing you report out at the end of the day. All right, let's see, where does that get us to? Right. The haters are going to hate. Is that the right number of hates? I hope so. So this is not without controversy. Back in the day, and I remember this because I'm somewhat old, there used to be fervent argument and animosity between people who wanted to do statistics in a Bayesian way and people who wanted to do it in a non-Bayesian way, and primarily a so-called frequentist way, which is what you typically will see in an introstat course, confidence intervals and hypothesis tests and so on and so forth. And literally, I can remember, again, grad school in the early 90s, you would hear these anecdotes about, so-and-so went and gave a Bayesian talk at the University of Toronto. Isn't that person brave? Because it's like going into the lion's den. Or in the other direction, so-and-so went and gave a frequentist talk at Imperial College London. That's a very risky move. So people used to argue way more than they do now about which way we should do statistics. My anecdotal observation is that we don't really do that so much anymore. I think we are just more pragmatic, and we don't try and pick these fights between the Bayesian and the non-Bayesian camp. And I think really that's because everyone can compute things now. And I'll get back to computing in a few minutes, but there's just more computing power, and both sides get on with actually doing stuff. And that's probably more productive than kind of fighting with each other and casting aspersions. And so, things have calmed down. However, there's still active sort of push and pull about, is this Bayesian thing a good thing to do, bad thing to do? So I'll talk about two potential criticisms of the Bayesian approach to things. And the first is that some people would find the computational engines that we use to do Bayesian inference. Well, I put meh on the slide. This isn't really fair. People have built amazing algorithms, just the problem's really hard computationally. And what do I mean by this? So ideally, you would want a piece of software that takes three things as inputs and gives you one thing as an output. You would like to put in your prior distribution, you'd like to put in your statistical model, you'd like to put in your data set, and you'd like to get as the output the posterior distribution over all these unknown things, right? Over the what we call the thetas. And so an ideal algorithm would be that the output is some sort of exact mathematical representation of the posterior distribution. I don't know. The posterior distribution is a normal distribution with a mean of 17 and a, something like that. That doesn't happen except in the most toyest of toy problems. Okay. And I guess, we did a calculation back on slide 2 or 3, whatever. That's also in the toyest of toy categories, right? We could compute exactly. So a near-ideal algorithm would be to replace a math representation with an ability to draw simulated realizations in your computer from the posterior distribution. So again, that probably means more to some of you than others, but you can kind of imagine, maybe the way I got this blue curve is I got my computer to simulate a million draws from the posterior distribution, and then I put this smooth density curve to match that. Maybe that's how that came about. However, we can't even do that. And so we have these software packages that, in principle, take these 3 inputs and give you this output. However, there's sort of some fine print. And, I'd use jargon here. So IID, for those unfamiliar, IID stands for independent and identically distributed. So meaning that you could just get your computer to, draw things that are independent and identically distributed. Yes, I'm going to get myself in a tizzy if I try and explain this. So nice, simple draws from the posterior distribution. Say it that way. Actually, if you read the fine print, all that's possible algorithmically is that your output is a large number of draws after some burn-in period from a simulated Markov chain whose stationary distribution is the posterior distribution. That's a little bit off-putting from an applied user's point of view. You think, what's that? Well, it turns out that's really the best we can do, and probably the best we can ever do. There are good reasons to think this is a computationally really, really hard problem. But I raise this just, some people don't like this. Or it's not that they don't like it, they will put it in the con camp, right? Oh, I want to do this Bayesian thing. It's going to take me hours of computing, and it might be a bit fiddly. So that's a legitimate concern people raise. Even though people work hard on building these general purpose software packages, and I should particularly give a shout out. I have some amazing colleagues in the stat department who work on these kinds of software and algorithmic developments. There's something called Blang, which is built by my colleague Alex Bouchard-Cote, and there's something called Pigeons. Don't ask me why it's called Pigeons. Actually, don't ask me why it's called Blang for that matter either. Alex and my colleague Trevor Campbell teamed up to build this Pigeon software. So people are really working hard on the computational side of things, and they're making progress, but there's some fundamental limit that you kind of have to do something like this. You don't get nice, simple IID draws from the posterior in your computer, and so that is a limitation. And then the other kind of funny thing is, and this maybe speaks to the problems of science happening in silos, and maybe speaks to why it's good to have these kinds of events where people from all different parts of the university are here. Even this so-called Markov chain Monte Carlo stuff, the stat community didn't get its act together on this until about 1990. And so in fact, how many times am I going to say this? When I was in grad school, this was kind of a big new thing on the horizon. And the funny thing about it is that there were 40 lost years in there because the physicists were all over this stuff 40 years earlier. Question?
Yes. So could you briefly explain what's burn-in means and what is a Markov chain?
Yeah. Oh, I was afraid someone would ask me that. Okay, so I will try. Okay, what's a good example? A Markov chain means that when you want to get the first draw from your posterior distribution, then you want the second one, and then the third one, and so on. And ideally, go back to the ideal or the near ideal. Ideally, you draw the first one from the posterior, and then You draw the second one without any reference to the first one. It would be independent of the first one. And then you draw the third one without any reference to the first and second, and that would be a nice ID sample from the posterior. And the theory is very simple. It says as you draw more and more of these, you know the distribution. We can't do that, and there are good reasons we can't do that. And so you get into this business that the only way you can make this work is by drawing the second one in a way that depends on the first one, and the third one in a way that depends on the second one, and so on and so forth. So that's the Markov chain part of it. And then that also means we can't draw the first one, because there's nothing behind it in the chain. And so we rely on this theory that says that a Markov chain converges to its stationary distribution. And Cindy's laughing at me because I'm making a hash of what stuff she knows way better than I do. It's just, it's a hard problem, and this is the best we've got, and it's imperfect. But it can be made to be pretty reasonable. So I'm being equivocal here, but the computation can be challenging. I would kind of leave it at that. The interesting anecdote here, getting back to the physics and so on and so forth, is that, two things. So most of these computational algorithms fall within a class of algorithms that nowadays are known as Metropolis-Hastings algorithms.
Do you mind if I just a quick
yeah.
question? Are these algorithms the best we can do, no matter how simple the class of prior distributions we?
No. So that's a really good question. If we make things really simple, like I did on slide 2, then we can do closed form calculation, or there's some other edge cases where we might do something better. But for anything of sort of reasonable statistical complexity, this is the best we've got. Okay, so anyway, so the kind of interesting historical anecdote, two things. Metropolis-Hastings algorithm. Well, Metropolis and Hastings didn't work together. Metropolis started with a Metropolis algorithm. I think that paper was maybe 1951 or something. And the interesting thing about Metropolis is that he could have been portrayed in Oppenheimer. He was in that orbit, the atomic bomb, Los Alamos orbit. I don't think he got an actor to play him, and he wasn't cast, but he could have been. And then 20 years later, Keith Hastings picked up on this and refined it a little bit and published it in a stat journal. And those were two big advances, although no one noticed for another 20 years. And so again, problem with silos. But the interesting thing about Keith Hastings is that he was local, or at least he ended up being local. I think he did his one and only published paper in about 1970. I think he was based in Toronto at that time, and then moved to Victoria and focused on teaching. I don't think he published anything else. Yet he's had way more impact than I, for instance, could ever hope to have. So it's kind of an interesting historical note. All right. So that's one criticism, is that there's been a lot of progress on trying to do this computation in a clever way, but it's fundamentally challenging, and it doesn't scale well with how many components you have in this theta, the dimension of the parameter, and it doesn't scale well necessarily with the size of the data set. And so that's just something we're stuck with. And then the other criticism you hear is that there's too much specifying to do if you want to do a Bayesian analysis. And the sort of flip side of that is you might get your specification wrong. And what do I mean by that? Well, there's no sort of shortcuts in a way. You have, if you want to do this, you have to have a prior distribution that is a joint distribution over all the unknown things in your problem. All the thetas, all the components within theta. And, could be some high-dimensional thing where theta has hundreds of components. And you have to think about how am I going to structure a prior distribution on that thing. And then you need the statistical model specification that is a conditional distribution for all elements of the observable data D given theta. And again, there's no sort of shortcuts. You have to have a fully specified conditional distribution, which in a way is even worse than the prior, right? Because that's not just one distribution, that's a family of distributions indexed by theta. And so that is demanding if you want to do complicated science problems. And it's kind of in contrast to a lot of what you see in the non-Bayesian stat literature is people get really excited if they cannot make these kinds of specifications. And there are these words that float around in our world, like being semi-parametric or non-parametric, which is trying to say, well, I don't want to have to make all these specifications of distributions because I might get them wrong. Or it's hard, or some combination of those two things. And again, there's some truth in that criticism. I'm not trying to minimize it. On the other hand, I will push back a little bit. And let's not worry about the model part. Let's just worry about the prior. So priors come in for a lot of scrutiny from non-Bayesian. Oh, what is this prior distribution? What is very amorphous, and is it a real thing, and blah, blah, blah. Well, I think the thing to bear in mind, or one thing to bear in mind, is that virtually all statistical procedures have some sort of tuning parameters. And I don't know what different statistical procedures people might have encountered in the past, but you might have seen terms like a bandwidth or a strength of penalty or things like that you have to specify to make your procedure go. And in a way, a Bayesian is doing the same thing. It's just that the prior distribution is their tuning parameter. It's maybe a complicated tuning parameter, but it can be viewed as a tuning parameter. And so in a way, it's not quite as different from other kinds of statistical techniques as you might first think. And then the other thing I keep coming back to is an old decision theory result that I think has been a little bit forgotten. But the paraphrase of this result, I think maybe goes back to the 70s or maybe the 60s, I'm not even sure, is that there's a theorem that says a statistical procedure is not clearly crazy if and only if it can be represented as a Bayesian procedure with respect to some choice of prior distribution. And so that is, for someone like me, that's very encouraging because it says, okay, the class of not crazy procedures is the class of Bayesian procedures that's indexed by your choice of prior distribution. And I find that somewhat comforting as well. For those of you who have seen some decision theory, you probably recognize that what I'm calling not clearly crazy is more commonly referred to as admissible. That would be a better technical term. And then I'll say a little bit more about specifying a prior distribution. In my world, at least, it's very common to try and specify what people might call a ballpark or weakly informative prior distribution that is not super spiky, not trying to infuse a lot of prior knowledge, but trying to infuse some. And that works okay in epidemiology in particular, just because we basically know, based on decades of research, that a field like epidemiology is riddled with weak associations and very rarely finds really strong associations. And so, for instance, if you're talking about the strength of a relationship between a binary exposure variable and a binary disease variable, that strength of association would typically be characterized by a so-called odds ratio. And kind of the zeitgeist in epidemiology is that, yeah, odds ratios, well, many of them are in many cases, there's no association, so the odds ratio is actually 1, or maybe it's very weak, 1.1, 1.2, 0.9, 0.8. Seeing 2s or 5s or 10s or halves or fifths or tenths very seldom happens. And so that gives you some sort of anchor to put in a prior that says that, right? My prior is, by the time we get out to 5 or 10, my prior will be quite low. It'll be quite spiky, potentially up close to 1. And so it's not completely made up, I guess is my point in that kind of context. And then the other thing I would say is I've not really had experience with this, but there are certainly people out there, papers and people who talk about doing formal prior elicitation. And the idea there is that you have sort of a protocol of the right questions to ask, and you sit down with your expert in whatever it is, multiple sclerosis or this other disease or this other disease, and you ask them the right questions, and in that process, you get their prior distribution out of their head and onto your piece of paper. And that's kind of a neat thing to think about. I don't think it's very easy, but I think it's a neat thing to think about. Or even more complicated, you try and form a prior distribution that is not based on one expert's opinion, but trying to reach some sort of consensus amongst a bunch of experts. And you can imagine that being quite challenging. But people work on that. All right.
A group of experts or several experts?
Uh,
I can't imagine asking a group.
Well, I think sometimes it's a group. People talk about, I'm going to convene this group of 5 oncologists and sit them around a table and ask them, yeah. You can imagine how fun that would be. But, I mean, it's not crazy. If they don't agree, your prior will be wider if you're trying to represent the group. And if they do agree, it'll be narrower. So it's not the most crazy thing. I think it would be, I've never done it myself. I think it would be hard, but it's a thing. Put it that way. Okay, so for the last part of my talk, this is now miles out of my lane in a way, but you could ask the question, do people use Bayesian reasoning in real life? Right? When I'm walking around stepping in puddles or not stepping in puddles, am I thinking in a Bayesian way about where to put my foot, things like that. Well, I have in a way, I'll say this, I guess. I'd say no, not if they're in a hurry. And what do I mean by that? Well, okay. To this day, I can't do this problem in my head. I can't do it approximately, I can't do it quickly, I can't do it heuristically. And the problem is just the one we had on like slide 2 or whatever, right? Except I've changed the numbers, right? So we went through the calculation when the prior was 1 in 100 and the sensitivity was whatever it was, 96, and the specificity was 98, I think it was, and we got the answer, that's fine. If you change those inputs, I can't do this in my head. I need a pen and paper. Okay? And in a way, I'm a statistician. I think I ought to be able to do this in my head, but I can't. Okay? Question?
Would a frequentist say, yeah, okay, if you give me this data, I can just do this problem?
No, I don't think so. I think,
it's more a sort of general.
It's more general. I'll come to that in a minute. Yeah, but I guess the point is that if we're in a hurry, I don't think we can we can't do Bayesian reasoning in real time as we're moving around the world. That's my take on it. And of course, there may be an evolutionary pressure against Bayesians because if you do hear a rustling in the grass, you may not want to take out your pen and paper and work out the chance that noise is coming from a tiger versus something else. So, this doesn't work in real time, right? But I'm not the only one who feels this way. And this, as kind of a last thing, I'll talk a little bit about one of my favorite books, probably a book some of you have read also. It's very well known, Thinking Fast and Slow by Daniel Kahneman, the late Daniel Kahneman. By the way, a UBC connection here as well, I think. He was on faculty here. 78 to 86, I looked up today. When I first read this book, I guess it's maybe almost 15 years old now, I'm not sure, but I found this extremely liberating. And the reason I found it extremely liberating is that about on page 5, he talks about some of the work he did with his colleague Amos Tversky. And they gave some kind of scenario questions to a group of so-called experts, including 2 authors of statistical textbooks. And they were along the lines of, you don't get a pen and paper to work things out. You just have to, take some statistical type questions, and based on your immediate judgment, provide an answer. And of course, everyone flunked, or most people flunked. And his concluding line is that even statisticians were not good, intuitive statisticians. So I don't think anyone can really reason in a Bayesian way in real time as they, or not completely anyway, as they kind of navigate around the Earth. So that said, I guess I'm down to my last slide. And I was trying to think how to wrap this up in a balanced way. So good old Bayes' theorem that talks about the distribution of the unknown theta given the observed data d based on the inputs that are the other way around, the model that tells you how the data is distributed given the theta, and the prior that is the distribution over the theta. And the best I could come up with is that Bayes' theorem is demanding but righteous. And it's demanding in the sense of these first 2 bullets that we've talked about. It requires, there are no shortcuts in a way. It requires a full specification of distributions for everything in your problem. For theta and for d given theta, for the data given theta. And it's demanding at different scales in terms of computing. Just as we were talking about a minute, it requires lots of compute cycles in your brain if you're trying to figure out, whether to step in the puddle or not. It demands lots and lots of CPU cycles on your laptop or the server or whatever it is if you're trying to do a large-scale scientific application. So demanding in those first two senses, but it's righteous in the sense that it's a way. I almost put the way, but I didn't know if anyone from the philosophy department was here, and I worried. So it's a way to be kind of definitive and universal in how you characterize what you do and don't know about the unknown parameters or the unknown state of the world after you've observed some data. And so on that note, I will close, and thank you very much for your attention.